We had talked about the gyroscope. If it has a angular momentum of L, this is the z-axis. It's at the angle of theta. There were several, I said, where we had analyzed how it moves. The question was, it can precess around the z-axis. It's at the top which precesses around the z-axis. The motion which goes around this way is called nutation. Nutation means that it's not stable. It's not a smooth operation. It goes around that circle, like in the diagram that I showed you of Feynman, in Feynman's book. Several students came to me and said that there is a motion which is smoothly just going around without nutation. I didn't believe that, but I went back and went through a complicated analysis. They were right. It's possible to have that motion, and the final formula is like this. mg is the weight of this body. This rod is supposed to be weightless. The length of the rod is supposed to be L. Theta is this angle. Theta can be 90 degrees, but it can be bigger or smaller than 90 degrees. Capital omega is the angular velocity around the z-axis if it goes smoothly. I2, this this gyroscope has a I1, which is the main one, but they can have, it has three angular momenta. I mean, it has three principal axes of inertia, and one of them is I1, the other two are I2 and I3, which are supposed to be the same. Then it can have this formula. If cosine theta is 0, namely if theta is 90 degrees, this becomes exactly the formula that I had derived in class. But at that time I thought that that's only an approximation. For theta equal to 0, I thought it's an approximation. Even for theta equal to 0, I thought it's an approximation. But after a careful analysis, it's not an approximation. For theta equal to 0, it was exact. Next, we discuss on a rigid body. If there is a complicated rigid body, it has a center of mass. Now, every part of the body is attracted by gravity. This is the real situation. Every part of the body is subject to gravity, depending on the density. If there is a particularly heavy part of that body, then the gravity here is higher. We now want to prove a theorem that the total effect of all these gravitational forces on different parts of the body is equivalent to one force acting only on one point, the center of mass, and with a magnitude proportional to the total mass of the body. So let me theorem. The total effect on a rigid body by gravity is equivalent to that of a single force with magnitude sum of m g on the center of mass. The total effect of on a rigid body by gravity is equivalent to that of a single force with magnitude summation of m times g on the center of mass. This is true for a static situation. Or a dynamic situation. Static situation 就是说它不动 if it's at rest. For a dynamic situation, if it's moving. For either case, these two cases are equivalent. And this requires a proof. We had proven that the motion of the center of mass, the acceleration of the center of mass, is equal to the total external force. We can write down the total external force as the total external force consists of two kinds, gravitational force and non-gravitational force. So I separate and write this. This is the gravitational force on the ith particle. This is all the other forces on the ith particle. So I separate the gravitational force from the non-gravitational force. And we also have the equation of d dt what is in the bracket is the total angular momentum. The time derivative of the total angular momentum is equal to summation of Ri cross Fi external. And we now separate that into two parts. Summation of Ri cross Fig plus summation of Ri cross Fi other. In other words, we separate the gravitational effect from the non-gravitational effect. These are the gravitational effect. What we now want to prove is that this gravitational effect is equivalent to the case where there's only one force acting on one point, the center of mass. But Fig, the gravitational force on the mth particle is equal to minus, suppose k is the unit vector on the z-axis upwards. So it's Mig times k. The gravitational force on the ith body is obviously equal to this. So summation of Fig is equal to minus summation of m gk, which is equal to total force on center of gravity. So this part is the gravitation. We have proven for this part that the action on the whole body is equivalent to the action on the center of mass. How about this part? Summation Fig is equal to R is equal to mgmk. So that is equal to R but summation of MIRI is equal to summation of m times R center of mass. This torque is equal to let's write the torque. This is the torque due to gravity. Is equal to minus g summation of m r center of mass cross k. And that is equal to torque on center of mass by one force, by so QED. Because we have proven that this term for the motion, dynamic or static, is equivalent to the action of one force, and this is also equal to the action of one force. So what's the conclusion? The conclusion is that when you talk about the gravitational force on a complicated, rigid body, you can replace the total effect by just one force on the center of mass. As a matter of fact, that center of mass may not be a part of the body. You can think of a ring as if a ring, the center of mass is here. It's not a part of the body, but the total gravitational effect on this ring is equivalent to a force of this. You can imagine that this is connected to it by a massless rigid rod. However, what we have proven is dependent on the fact that every point is attracted by Earth with a magnitude of m times g, and it's always the same g. If it's a big body, this is not correct. If this is the Earth, if I think of daily life, that statement that every particle is attracted in the minus z direction with mg is correct. But if this is the Earth and you have a big body like a mountain, then the force here and the force here are not even in the same direction. As a consequence, the theorem that we just had proven is true only for small bodies. As a matter of fact, I can easily construct a case where you have a collection of forces on a body, and that collection cannot be replaced by one force. What we have proven in the last sheet is that the collective forces, gravitational forces, if it's a small body, is replaceable by one force. But in general, it is not true that if I have a collection of forces, if I have one force which goes this way, another force which I only need two forces. If these two forces intersect, then you can replace these two forces by one force, which is the sum of the two. If those two forces do not intersect, for example, if one goes this way, the other one goes this way, then it is not possible to replace it by a force. You can take the sum, but the torque would not be correct. So in general, a big body, like this case, the total effect of the gravitational force on that big body not only is not replaced by that formula, it can, in general, it cannot be replaced by a single force. It has to be replaced by more complicated. Can anybody tell me, if I say that, okay, if I have a complicated collection of forces, I said it may not be replaceable by a single force. Could somebody tell me whether it can be replaced by somewhat more complicated arrangement? It can be replaced by two things. A, the total force. You just add all the forces like what we had. But the components may not be parallel to each other. And B, plus a torque. A torque is just, you can think of two equal and opposite forces, this way and this way. That generates a torque. Theorem any collection of forces acting on a rigid body, a complicated rigid body, can be replaced by one force on the center of mass plus one torque. But we are not going to use this theorem, so I just stated. If you are interested, you can think about it. It's actually not difficult to prove. There is a concept called the center of gravity. Center of gravity is not the same as the center of mass. Center of mass only depends on m. It doesn't have anything to do with any forces on it. But center of gravity, if you want a definition like this, is that you try to take a point where one force acts on it, and that effect of that is equivalent to the total gravitational force. That in general does not exist. Center of gravity is the center of mass if the body is small. Center of gravity for a large body does not exist. Because the collection of gravitational forces on a large body cannot be replaced by a single force acting at a single point. Now we are going to do one of the problems of the book. It's page 291, 24p. A series of 4 blocks of the same length. They are each of them uniform, and you put them at the edge of the table. And the question is, you try to make them as far away from the table as possible. So this is called A1, A2, A3, A4. You want to make each of them as large as possible. The question is, what if the total length is L? What are the values of A1, A2, A3, A4? Well, first, in order to make this problem simple, let us choose L to be equal to 4. That makes it easier to think. So let's first analyze the top block. I think everybody would agree that the top block is such that the A1 is equal to 2. Because if this third block is already stable there. You put the force on, and clearly if you make it just halfway going out, it's just balanced. So we say A1 is equal to 4, or is equal to 2. Then let us consider A1 and A2. Consider the top two blocks together. The center of mass of these top two blocks is here. Agree? It's symmetrical. So if I put that, if I put the next block here, the top two blocks won't fall. That proves that A1, A2 is equal to 1. Then we consider the center of mass of the top three blocks and put the next one here. In other words, what we have just done is the following. To determine this point should be at the center of mass of the first block. This point should be at the center of mass of the top two blocks. This point should be at the center of mass of the top three blocks. Is everybody happy with what I just said? Okay. So in order to do this systematically, let's take this point to be the origin and call this distance x1. x1 is the center of the position of the center of mass, always referring to this point of the top block. This we call x2. x2 is the position, is the x coordinate of the center of mass of the top two blocks. And this one we call x3. x3 is the position of the top three blocks. So we know x1 is equal to 2. How about the x2? x2 here is the center of mass, is the position of the center of mass of the top two blocks. By definition, 2x2, we assume each block to weigh exactly 1. So the top two, that should be equal to MIXI summed. So MIXI summed is equal to x1 plus x1 plus 2. I'm now talking about, I'm calculating this point. So this is the center of mass of the top two blocks. So this is sum of m times the x of the center of mass of the top two blocks is equal to m1x1 plus m2x2. All m's are equal to 1, so it's equal to x1, the position of the center of mass of the first block, that's x1. The position of the center of mass of the second block is x1 plus 2, because you have moved by 2. So I get 2 x2 minus x1 is equal to 2. So x2 minus x1 is equal to 1. So I have x2 is equal to x1 is equal to 2. x2 minus x1 is equal to 1. Now I do the same for the next one. The next one, I have the x3. x3 is the position of the top of the center mass of the top 3 blocks. So I get 3x3. I'm now writing a summation mi xi is equal to sum of m times x of center of mass. So sum of m is 3 because I have 3 blocks on top. This is the position of the center of mass. And that's equal to, we had proven a theorem earlier that if you have a collection of particles, you divide into 2 groups, then the center of mass of the whole thing is equal to the center of mass of 2 particles. One is the center of mass of this group. You think of this group to be concentrated at one point. You think of this group to be concentrated at one point, so that you have only 2 particles. And then the center of mass of these 2 imagined particles is equal to the center of mass of the whole thing. We have proven the theorem. So now we use that theorem. So the 3 blocks, I first do the 2 of them. Now 2 of them I get, of course, 2x2 I get, of course, 2x2 plus the third one. The third one is at x2 plus 2 times 1. So if I do this, I get 3x3 minus x2 is equal to 2. So I get x3 minus x2 is equal to 2/3. If you think about this, it's actually 2 seconds. Now if you do this next, you get x4 minus x3 is equal to 2/4. x5 minus x4 is equal to 2/5. So successively, these a's are equal to 1. The next one is 2/3. Then it's 2/4, 2/5. Everybody happy? Anybody unhappy? Okay, now we get so if you have an enormous number of these, what do you get? You get, it's extending. If I want to calculate how far it extends beyond the edge of the table, I get 2, it's actually 2/1 plus 2/2 plus 2/3 plus 2/4 plus etc. is equal to 2 times 1 plus 1/2 plus 1/3 plus 1/4. Who knows what that infinite series is equal to? This is a famous series. It's equal to what? It's equal to infinity. Does anybody know how to prove that? Raise your hand. Who knows? Don't be shy. Yes, the proof why that is infinity.
I consider the graph under y, the area of graph under y equals to 1/x.
Okay. What this student says is he considers y, this is x, he considers the curve y equal to 1/x is a curve like this. And I think what he wants to say is let's say this is a number, let's say, the way that I draw it, this has to be maybe 5 over 1, so 5 over x, and this is 5. At 1 is 5, at 2 is 2.5, and this is the first area, this is the second area. And that's correct, but that's how do you know that this area is infinity?
Because the area under the graph from 1x equals to 1 to x equals to infinity is the integration of 5 over x. The x will give you 5 log x.
What it says is it's not incorrect. But it's too complicated. It's much simpler. Can anybody give me a very simple proof that that's infinity? Yes.
这个数列等于，就是不是等于，往上来。您再写这数列是1加1/2。刚刚那个数列是这样。
所以呢，
这个2个是1/2，它是很多1/2加起来。
对，就是你叫李真是不是？李真说这个 this is the series 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on and so forth. Now he wrote another series which term by term is smaller than this one. This is 1/2, this 1/3. He writes 1/4. So these two are 1/4. These 4 he writes as 1/8. And the term by term, this new one is smaller than the old one. But these two together is 1/2. These 4 together is 1/2. The next 8 together is 1/2. So there are infinite number of 1/2s, which is evidently as large as you want. And this is larger than this as large as you want. So it's even larger. So it's infinity. Actually, this proof is exactly the same as what that fellow wanted. Only you do it this way. Instead of take this, you take this. So therefore, all of this is more complicated. But this way of reasoning goes by doing something like this, and then you need to prove that the sum is bigger than is as large as possible. You can go through the same argument. What that fellow wanted is a logarithmic. This curve, when you integrate it, becomes a logarithm, and logarithm of infinity is infinity. So that's another proof, but that proof is a more complicated proof. Li Zhen's proof is the simplest. So, in principle, you can make it lean as far as possible. But of course, in practice, you can never do that. It will fall out if you try it. If you have several books, you easily find that unless you make very accurate blocks, you cannot make it extend very far. Now, if we have a static situation, that means no motion. That means all time derivatives are zero. In that case, acceleration is equal to zero. So we have two formulas. One is the sum of Fi external. That, of course, includes gravity is equal to zero. And sum of Ri cross Fi external, the total torque is equal to zero. For a three-dimensional case, this is three equations, this is three equations. So you have six equations. Let me emphasize that in doing this, you can replace, we have proven that we can replace the gravitational force by a single force, since we usually talk about in daily life small objects. And the other one is that you have to be careful that only include external forces on the body, not forces by the body on other things. The reason I say this is because I had taught freshman physics in Stony-Brook, and one of the great confusions in solving these equilibrium problems by the students was that some students get confused about they include some of the forces exerted by the body on other things. If your problem has several bodies, you have to be careful that you look at each body separately and look at the forces on that body and not forces by that body on another body. So remember this point. For a three-dimensional problem, we have three equations here, three equations here. We have six equations. So if the problem starts with six unknowns, in general you can solve for the six. But there are cases where if there are too many unknowns, then if there are more unknowns for three-dimensional problems than six, then you have a case where you have no unique solution. But you don't have to count it that way. Let's, for example, take a simple case, which is a four-legged stool. If I have a four-legged stool and the whole body has a weight here, and you are asked to evaluate the four forces on the four legs. The body suffers five forces. One is the gravity in the center, and then the four forces on the four legs. So you have F1, F2, F3, F4. You have F1 plus F2 plus F3 plus F4 is equal to mg. If you take the angular momentum, you get suppose this distance is called r. This diagonal distance we call it r. Then let's this one be F1, this F2, this F3, this F4. Then F1 and F3 I claim F1 minus F3 times R is a torque in this direction, and that has to be equal to 0. While F2 minus F4 times R gives you a torque in a perpendicular direction. So that also has to be equal to 0. Does everybody agree with these three formula? It's a rectangle. So the F1 and F3, one gives a torque this way, the other gives a torque this way. So you have a torque which is in a diagonal direction. F2 and F4 gives a torque in a perpendicular direction. And since the vector has to be equal to 0, so both components have to be equal to 0. So we have these two. In this case, you have only three equations, and you have four unknowns. So therefore, it's indeterminate. In fact, what this equation says is that F1 is equal to F3, F2 is equal to F4. And for example, I can make F1 equal to I can make, for example, F1 equal to F3 equal to 1/2 of mg, and F2 equal to F4 equal to 0. In other words, the first one and the third one, diametrically opposite one, equal forces, and the other two have no force. Actually, intuitively, you know this is the case. If it just it's the case where only these two touch the ground. If these two do not touch the ground, then these two forces exactly each of them becomes 1/2 of mg. But if these two touch the ground and these two do not, then you have the other solution, which is the opposite of this. And you can have any linear combination of them. So if you have a smooth floor, if you put this heavy stool on it, what happens? You know, all four of them would have the same weight. In other words, the true solution for a physical situation is each of the forces, F1 to F4, is equal to 1/4 of mg. How do you know? Why do you believe that all four are equal for a real situation? It is because there are other things that you have to consider, and that comes to elasticity. ground is slightly elastic, and if one leg goes down too much, there will be a tremendous force forcing it upwards. So if it is an elastic thing, so think of a rubber floor, then it will become, then it is, if you want really to analyze this, it won't be that one sinks deeper than another one. The simplest case is all four of them to go down by the same amount, and therefore the reactions force F1, F2, F3, F4 would also be identical. So if you want to consider a physical case of over-determined system, then you have to consider the property of the surface. If the surface is uniform, like a rubber or a soft floor, then of course you would get equal ones. But if the floor is such that two of the legs are on rubber, the other two legs are on a hard floor, you immediately know what happens. The part on the two legs would sink deeper into the rubber, and therefore the thing would tilt, and the forces would not be identical on the four legs. So in that case, you need the elasticity. So next we turn to the elasticity question. In the book, it's section 13.6. The book discusses three kinds of stress and strain. First is the Young's modulus. If you have if you stretch something, if a cable, you stretch it by delta L. The original length is L. Delta L is the amount you stretch. Then the force is always proportional to the area. If it's a steel cable or if it's a steel rod, if you stretch it, the thicker the rod, of course, the larger the force. So it's the force per unit area that's important. Force per unit area is equal to a constant, which is called Young's modulus, times delta L over L. This is called Young's modulus. You should read the table 13-1. It lists the Young's modulus for steel, for aluminum, for glass, etc., etc. Look at it, you will see that the larger the Young's modulus, of course, the larger the force per unit area. For steel, the Young's modulus is very large. As a consequence, you cannot stretch it very much. It requires tremendous force to stretch it. By the way, this formula also is correct for both plus sign for delta L and minus sign for delta L. If delta L is positive, that means you are stretching it. If delta L is negative, that means you are compressing it. Stretching it and compressing it, if the stretching and the compression are not very large, it follows the same formula. In other words, the same Young's modulus always works for both stretching and compressing. But that's true only for small displacements. If you stretch a steel rod too much, it will break. The precise behavior of a steel rod when you stretch it is an extremely important topic, because if you are an engineer, you have to know what happens. For example, a suspension bridge depends on stretching a cable. And if you stretch the cable too much, it would break and the bridge would collapse. So therefore, if you study engineering, you would need to know the behavior of steel rods when the stress and the strain become too large. And so read that section of the book. It has a diagram which indicates experimentally how, when you stretch too much, the rod would break. Now, does one understand that curve? To a certain extent, but the fundamental understanding becomes extremely complicated. Why? Because a steel rod is a crystal. Now, you can have a perfect crystal and a non-perfect crystal. And when you stretch it too much, or when you compress it too much, the crystal becomes distorted. But actually, a rod is never a perfect crystal. It has defects. And when you try to stretch it or compress it, these defects rearrange themselves. So that's an extremely complicated subject. And if you study engineering, you'll be dealing with such things. Or rather, it's like this. If you study solid-state physics, you will deal with such things. If you study engineering, you will also deal with such things, but from different viewpoints. For a physicist, you will be dealing with, for example, the defects. When you stretch it too much, you would have rearrangement of the defects, and that's a very complicated, very fascinating subject, and there are people who devote their lives to it. If you are an engineering student, you do not care about how precisely it goes inside, but you want to know the phenomena. What kind of steel would have what kind of a stress-strain curve, and you base your judgment about how to make cables or how to make buildings on such phenomenological curves. So it's the same complicated subject, but viewed from different ways by a physicist and by an engineer. Now, another one is shear modulus. If you have a block with a length of air, instead of stretching it or compressing it, you can shear it by making it move this way. You anchor it. This point is clamped, and you instead of compressing it or stretching it, you shear it, and this distance is called delta x. In that case, the force per unit area is again force per unit area is equal to a shearing stress, a shearing modulus times delta x over L. And the book also talks about the hydraulic stress. That is, if you have if you put a rubber ball, if you move that rubber ball deep into a swimming pool, it will be compressed. And if a diver takes that down to very deep depths, it will become much smaller. And if you take a steel ball, it's not going to change very much. But if it's under tremendous pressure, it will still be compressed. And in that case, the pressure is equal to a Burke modulus times change of volume divided by volume. The book talks about these three, but actually the problem is much more complicated than this, because we talk, for example, about the stress and strain. The stress and strain are not just a vector. Take this case. The displacement is in this direction, and the force could be in more than that direction. This is a simplified case. So in general, the stress and strain are both tensors. Tensors are more complicated than vectors. So therefore, the relationship between stress and strain is a very complicated subject. And that itself is a subject which has been dealt with both from the physicist viewpoint and from the engineering viewpoint. Okay, now we are going to leave chapter 13 and go to chapter 14. Chapter 14 talks about the gravity. The gravitational force between 2 points is equal to, we usually write a minus, and the gravitational constant times the mass of the first one, mass of the second one, divided by r squared, where g is equal to 6.67 times 10 to the minus 11 Newton meter squared divided Newton meter squared divided by kilogram squared. Actually, that the gravitational force between two things is inversely proportional to distance squared was already guessed at around Newton's time. We, in general, attribute the beginning of modern science to Newton's work called the Principia. But of course, Newton was living in an environment in which, after the Renaissance in Europe, there were all kinds of intellectual pursuits, including, for example, the proof that we just used, that the 1 plus 1/2 plus 1/3 plus 1/4 and so on and so forth is equal to infinity. But much more complicated the formula than that were already known by complicated arguments by many people. So there was Renaissance. The Renaissance created a general atmosphere of intellectual pursuit, and Newton lived in that atmosphere. But he was, of course, a great genius, and we shall see how how great a genius he was in a few minutes. He was the one who formulated this formula. But as I said, it has already been guessed at by many people. Now, actually, when he was in his 20s, he already had this formula in his mind. But he did not publish it for 20 years. Why did he not publish it? Because he wanted to understand one thing, and that is, if there was already before him Kepler's 3 laws. I'm sure you have learned about that in high school. And Kepler's law says that if you have a sun here and you have an earth here, then the earth would go around the sun. Well, this is a very bad ellipse. So Newton wanted to prove this, and we are going to prove this later. But Newton realized that the earth is not a point, it's a small sphere. The sun is not a point, it's a big sphere. And if he proposes the gravitational force, it's the gravitational force between every part of the sun and every part of the earth. So you should not treat the sun as a point and the earth as a point. He first proved that if there were points, then the earth would move in an orbit, which is an ellipse, which of course made him very happy, because that's what Kepler had proven experimentally. No, I shouldn't say that. Kepler used experimental data. Kepler analyzed experimental data and found for the first time in the history of mankind that the trajectory of the earth is of Mars. Actually, he was looking at Mars. Was an ellipse and not a circle. That was a great revolution. We'll come to that later. So Newton knew that. And Newton wanted to show that the big sphere attracting the small sphere gives you the same result as 2 points attracting each other. And that's the book called shear theorem. The shear theorem, this theorem took Newton 20 years. And after he has completely mastered that point, he wrote his book. Actually, there's another reason. There were people who were telling him that if you don't publish, other people would publish it. So he rushed into publication. That book is called the Principia, and that's of course one of the great events in the history of mankind. Now, what is the shear theorem? The shear theorem says that if you have a shear, you have a uniform shear, then if you have a gravitational force by the shear on a body here, then that gravitational force is equivalent to you compress all the shear's mass into one single point, and you use the same formula, same gravitational formula of attraction between this center and this point. In other words, the shear, as far as the gravitational attraction is concerned, can be replaced by a single point. That's called the shear theorem. Now let's try to prove that. Suppose this distance is r. This distance is a. A is the distance from the center of the point P. This is the center, point O. And let us now consider a ring at an angle theta. So now we consider this ring. We consider instead of the chair, a part of the chair, just a ring. Let's call this angle phi. This angle is theta. What is the area of the ring? The circumference of the ring is 2 pi r times sine theta. R sine, the ring is a circle. Its diameter, its radius is r sine theta. So 2 pi r sine theta is the circumference. So the area of that is equal to that circumference times the width of the ring. The width of the ring is r d theta. Agreed?像是个西瓜皮一块，这个 circle 是 2 pi r sin theta， 这个皮的那个宽度是 r d theta。这个 mass of the ring 呢，是，所以这是那 area。这个 ring 的 depth 假如叫做t， 它的 density 叫 rho， 那你就把刚才这个乘上 rho t。rho 等于 density， t 等于 thickness。这个是整个这 mass， 所以有这么多的整个这 mass， 这个 attractive force 呢向这个方向，所以 force by ring at P is equal to 方才这个东西 rho t 乘上这个东西。假如这个东西的 mass 是 m， 那乘上 gm divided by the distance squared。这 distance square 是什么呢？是 r sin theta squared。就这个 distance 的 square 是是 r sin theta 的 square 再加上这个的 square， 或者是加上 a 减去 r cosine theta 的 square。可是这个还不对，因为这个是 force 斜着的，它每一点这个 force 都有个 component along the axis， 所以还得乘上 cosine phi。Does everybody agree with this?可是我们知道 cosine theta 是什么 cosine theta 是等于 a minus r cosine theta divide 不是 cosine 是 cosine phi 是 a minus 这个 divided by the radius 是 square root of 刚才那 denominator。我刚才那个我叫 f， 所以 f 就等于 2 pi rho t r squared g m 乘上 integrate of sin theta d theta 乘上 a minus r cosine theta divided by square root of r square sine square theta 加上 a minus r cosine theta square 的三次方，这是 theta 等于0到 theta 等于派。这个I'm assigning this as an exercise. You know, one of the exercises next week, you'll be evaluating this integral. And after you've evaluated, you find it to be this 4 pi rho t r squared gm over a squared. But 4 pi r squared 4 pi r squared is the surface area of the shell. 4 pi r squared t is the volume. So 4 pi r squared t rho 等于 mass of shell. 我把这个叫做 m prime， 所以这就等于 m prime g m prime over a square. Therefore, the force is equal to the force exerted at the point P by a body at the center with mass equal to m prime. The shear theorem. So Newton assumed that the sun is a uniform. It only has to be spherically symmetrical. So many shears, and all of these shears can be compressed into one point, attracting the Earth. By a reversed application of this theorem, you can also shrink the Earth into a point. So therefore, you get the conclusion that you need only think of point motion for talking about such a dynamic problem. If you look at, I think I told you once, it's clear that is how he arrived at this. It took him 20 years to develop integral calculus for him to be able to do this. But when he wrote his book, he did not use integral calculus. He used geometrical arguments. I never understood the geometrical argument, but as I told you, Chandrasekhar, a great astrophysicist who died 10 years ago, spent the last 10 years of his life trying to puzzle out what Newton did. And he claimed to have understood the geometrical proof of this shear theorem. So this is the Earth. For a man here, the gravitational force has in the denominator the radius of the Earth squared. But if you have a mountain, for a man on top of the mountain, the distance to the center of the Earth is larger, and therefore the gravitational attraction is smaller. Actually, there's another added part to it. For a man here, the immediate if this is a high mountain like the Himalayas, the person here suffers a force not only by the Earth itself, but also by the mountain. So it's very complicated. But the main effect, these two effects are in opposite directions. He's been very high. The distance is larger, so therefore the gravitational attraction is smaller. But because of the mountain, his gravitational attraction is larger. These two are in opposite directions. But the former one is more important. So the gravitational force at this point is in general smaller than the gravitational force on the surface of the Earth. You can read that in the book. Now let's ask, what is the gravitational force inside the Earth? People now can dig a hole into the ground several kilometers, and you can ask, how about the gravitational force inside? Then there is another version of the shear theorem. The shear theorem, let's see, what did I write down the? I did not write down shear theorem. The gravitational force on a particle, on a point outside a shear, by the shear, is the same as if the shear is compressed into one point. At its center. Let me read. The gravitational force on a point outside the shear, by the shear, is the same as if the shear is compressed into one point at its center. 这个 shear theorem 还有另外一个 part， 你可以叫刚才那叫 shear theorem A、shear theorem 2、shear theorem B. The gravitational effect force exerted by a shear on a point inside the shell is 0. So, the point P suffers attraction this way, but it also is attracted this way. So, in all directions, it's obvious that the force exerted in the center is 0 because it's spherically symmetrical. So every force is balanced by another force equal and opposite to it. But for a point not in the center, it is not obvious that it's equal to 0. But Newton had proven that it is equal to 0. So it's also called a shear theorem. I will assign that also as an exercise for you. But both shear theorem A and shear theorem B can be very easily proven when you learn electricity. It's a fundamental aspect of electricity, and by more advanced concepts, it becomes you don't need any integration. You can immediately get the result. That is the power of higher mathematics. In fact, this remarkable phenomenon that from the outside you can compress it, the effect can be regarded as a compressed point. Inside there is no force. That crucially is dependent on the inverse square law. For example, you can do the same exercise that we did, but not with 1 over r squared, with 1 over r 2 plus delta. People have studied this. Instead of 1 over r squared, you write as 1 over r 2 plus delta. Then you find that neither theorem is correct. If delta is not equal to 0, then both the outside and the inside, the results are different, are very complicated. So in many senses, Newton was very lucky, because if nature did not have delta equal to 0, then it becomes much more complicated. He may never find Newton's law. But of course, if delta is not equal to 0, Kepler's law is also not correct. And if Kepler's law is not correct, then the whole problem, the thing would go around in very complicated orbits, and there will be no Kepler's 3 laws. Then there may be never develop the mechanics. Okay, so why was Newton so lucky? Or in many senses, why is mankind so lucky? If you ask this question, you find that it's because 1 over r squared law not only is simple when you write it as 1 over r squared, it's because it follows more general rules, and in those general rules, it has to be delta equal to 0. In other words, we now understand more why it has to be the inverse square, not the inverse 2 plus delta. But that still does not explain why this more complicated, beautiful structure was chosen by nature. So my conclusion is the following. It is indeed very remarkable that nature has successive layers of elegant and beautiful rules, which in some sense are made such that it reveals beauty. And that is the reason why we could decipher some of these. But you can never answer the last question, because if you find an overall structure which explains this 2 plus delta, you have to ask the question, why this overall structure ad infinitum? So I always say that what Newton taught us is that there is science, but science cannot explain everything. If you ask too many questions, science cannot answer it. That part belongs to religion, because the religious people say that's very simple, God made it. But that answer, in fact, is very profound. Profound in the sense that it can always be true. And so, in my opinion, science and religion are not contradictory. They are after the same thing. Only as time goes on, we understand more, so the territory of science expands and religion retreats. You know that Galileo was persecuted by the Catholic Church. Now the Catholic Church had to admit that they were wrong. They should not have persecuted Galileo. So religion is retreating. But religion forever will be bigger than science, because it covers everything beyond. And I believe that will remain the case forever. Okay, next time. I'm going to give you the result of your examinations. So I hope everybody did well. We had talked about the gyroscope. If it has a angular momentum of L, this is the z-axis. It's at the angle of theta. There were several, I said, where we had analyzed how it moves. The question was, it can precess around the z-axis. It's at the top, which precesses around the z-axis. The motion which goes around this way is called nutation. Nutation means that it's not stable. It's not a smooth operation. It goes around that circle, like in the diagram that I showed you of Feynman, in Feynman's book. Several students came to me and said that there is a motion which is smoothly just going around without the nutation. I didn't believe that, but I went back and went through a complicated analysis. They were right. It's possible to have that motion, and the final formula is like this. mg is the weight of this body. This rod is supposed to be weightless. The length of the rod is supposed to be L. Theta is this angle. Theta can be 90 degrees, but it can be bigger or smaller than 90 degrees. Capital omega is the angular velocity around the z-axis if it goes smoothly. I2, this gyroscope has a I1, which is the main one, but it has three angular momenta. I mean, it has three principal axes of inertia, and one of them is I1, the other two are I2 and I3, which are supposed to be the same. Then it can have this formula. If cosine theta is 0, namely if theta is 90 degrees, this becomes exactly the formula that I had derived in class. But at that time I thought that that's only an approximation. For theta equal to 0, I thought it's an approximation. Even for theta equal to 0, I thought it's an approximation. But after careful analysis, it's not an approximation. For theta equal to 0, it was exact. Next, we discuss on a rigid body. If there is a complicated rigid body, it has a center of mass. Now, every part of the body is attracted by gravity. This is the real situation. Every part of the body is subject to gravity, depending on the density. If there is a particularly heavy part of that body, then the gravity here is higher. We now want to prove a theorem that the total effect of all these gravitational forces on different parts of the body is equivalent to one force acting only on one point, the center of mass, and with a magnitude proportional to the total mass of the body. So let me theorem. The total effect on a rigid body by gravity is equivalent to that of a single force with magnitude sum of m g on the center of mass. The total effect of on a rigid body by gravity is equivalent to that of a single force with magnitude summation of m times g on the center of mass. This is true. For a static situation